In this lecture, we will see the schematic diagram of a AND or invert gate and how to draw the layout from the schematic. So this is a AND or invert, that is AOI 21 gate. AOI 21 gate. Now how do we represent a AND or invert gate? We represent it as Z is equal to AND, that is A dot B, or that is plus C invert is this. So it consists of AND plus or plus invert. Now the AND or inverter is drawn as, this is the AND gate. The input to the AND gate is A and B. Output is connected to the OR gate. This is A and B. This is the third input C. The output is A and B or C, and there is a inverter which produces the output A and B plus C bar. Okay. Now if you look for the truth table of the AND OR. Okay, before going to the truth table, if I say this is A or B, when it is A and B, when there's a dot operator, we know that the NMOS is in series and the PMOS is in parallel. When there's a plus operator, we know that the NMOS is in parallel and the PMOS is in series. So since there are three inputs, we need three PMOS and three NMOS, out of which A dot B, that is NMOS in series, so we'll have two NMOS in series and one in parallel. Out of these, we have two in parallel and one in series. Okay, so now we'll see the truth table of this gate. AND or invert 21 gate. This is A, B, then A dot B. Then we have the third input C. Then we'll see A dot B plus C. And then the output A dot B plus C whole bar. Okay. Now inputs are 0, 0, 0. A dot B is 0. A dot B plus C is 0. The output is 1. When it's 0, 0, 1, A dot B is 0. A dot B plus C is 1. So the invert will be 0, 0, 1, 0. Output is 0. Here again 0 and here 1. Then 0, 1, 1. 0, 1 output is 0. 1, 0 output is 1. Again the output is 0. For 1, 0, 0. 1, 0 again it's 0. Here it's 0. Here it is 1. Here it's 1, 0, 1. Output is 0, 1, 0. 1, 1, 0. And is 1. This is also 1. The output is 0. Then 1, 1 and 1. This is 1. This is 1. The output is again 0. Okay, now this is the truth table. Of a AND or invert gate. Okay, now let's see the schematic. Schematic diagram of a AOI 21 gate. AOI 21 gate. So as we know that the NMOS, that is basically we have to do an A dot B plus C whole bar. So for this portion the NMOS is in series and the PMOS is in parallel. Here for plus C, NMOS is in parallel and PMOS is in series. So for A dot B, the PMOS is in parallel. So it's connected to VDD. Okay. A dot B, so this is in parallel. and the third input C is in series with this parallel circuit. And just the reverse will be the pull down circuit, that is the first two inputs will be in series, it's not like that, and the third input just in parallel. So this is connected with this. This is the input A. The input C is connected over here. This is connected to ground. And the final output C is connected. I think the better diagram would be somewhat like this. This is connected to VDD. This is connected third input. Now here the NMOS is in parallel. So this A is connected over here. This is C, which is connected over here, and this is the V circuit. This is A, this is B, and this is C. From here you'll get the output Z. So this is P1, P2, P3. This is N1, N2, and N3. This is the source of P1, the drain of P1. This is the gate of P1. This is the source of P2, drain of P2, and this is the gate of P2. Now similarly, this is the drain of P, this is the source of P3, this is the drain of P3. Why? Because from the drain terminal you obtain the output. This is the gate of P3. Similarly, we have the output is obtained at the drain terminal, so this is drain. This is also drain of N1, drain of N3, source of N1, and this is the gate of N1. Similarly, this is the source of N2. This is the gate of N2, and this is the drain of N2. This is the source of N3, and this is the gate of N3. Now this is the normal schematic diagram. So this is the normal schematic diagram of AOI 21 gate. Now if we try to represent this in the twisted form, if you want to represent this in the twisted form, then that is called as the twisted schematic diagram of AOI 21 gate. So when there is twisted schematic, there are 3 PMOS. So first draw the 3 PMOS. You have to keep seeing the normal schematic and the twisted schematic. You have to keep tallying. These are the 3 PMOS, and you have the 3 NMOS. This should have been a bit this side. So now the first thing is to label, write it as P1, P2 and P3. This is N1, N2, N3. This is the source, this is the drain. This is again the drain, source. This is source and we all know these are the gate terminals. This is the drain, source, drain, source, source and drain. Now the gates are connected. The gates of PMOS and NMOS are connected, which gives the first input A. Then the second connection gives the second input B. The third gives the third input C. Now I have to keep tallying the normal schematic. So you know the first 2 PMOS were in parallel. So their sources are connected to VDD. Sources are connected to VDD and the drains were connected together. Now this common connected drain was connected with the source. So connected. Now this drain was connected with this drain. Before that, the source the source of N2 and N3 were shorted to ground. The source of the NMOS is connected to ground. P1 and P2 were in parallel, N1 and N2 were in series. N1 and N2 in series were both in parallel with N3. So now, since these two were in series, this drain of N1 and this drain of N2 were connected together with the drain of P3. So this is the output Z, that is A dot B plus C bar. So this is a twisted schematic diagram of a AND or invert 21 gate. Now let's see how to draw the layout from the twisted schematic diagram. Go to the next page. So we have seen the earlier layouts also. So now it's easy for you to draw the layout. So now let's see the layout of AOI 21 gate from the twisted schematic diagram. So okay, now there were three MOSes in total, 3 PMOS and 3 NMOS. The first 2 PMOS were in parallel with the third PMOS. The first 2 NMOS were in series and they were parallel with the third NMOS. So after seeing the twisted schematic, let's draw the layout. So at first you have to draw the anvil. You have to take a larger area. This is the anvil layer. Then you have the P diffusion layer. P diffusion layer is brown in color. We can represent the first 2 PMOS that were in parallel in 1, not because they were in series, but with some reason we are placing them in 1, and the third one separately. This is the P diffusion layer or the P dip layer. Then we have the N diffusion layer. This is the end diffusion layer or the end diff layer. Now, after drawing the layers, next you have to draw the terminals. So first you'll start with the gate terminal. Just got this one. This is the first gate and this is the second gate. Okay, now this is two input A and B. This is the third input. C. Okay, now have to connect. This is the source, gate and drain. Okay, similarly this is the source, gate and drain. This drain was connected to the source and drain. This is again the drain, drain, source, drain, source, source. These are the gate. Just compare this with the twistor schematic. Okay, now these two sources actually they have a common drain. That's why we have placed in a single P diffusion. Otherwise we would have taken different diffusion layers. So this is a metal layer. This is VDD. Now this common drain is connected with this source. So connect with the source. Now these two drains are connected together and this source is connected to ground. And these two drains okay, now these drain is connected. This common drain is connected with the drain of the PMOS. With this drain. Now this is the output Z. Okay, now this is metal 1. This is the poly layer. Now You have to place the contacts. Since the metal layer is connected with the P diffusion layer, so there will be a contact over here. That is the P diffusion contact. P diffusion contact, or it is otherwise called as PDC. This is the another PDC contact. PDC contact. This is another PDC. Then you have the N diffusion contact. This is the N diffusion contact. Or the NDC contact. Similarly, okay, after placing the diffusion contacts, you have to place the substrate contacts. This is one. You can place it as many as you want. This is the N substrate. When the side where there is P diffusion or N value, we have to place the N substrate contact, and while writing the commands you have to write it as NWC, that is N well contact. Similarly, you have to place some contacts in the ground layer. Ground and VDD, you have to place these contacts. So here this is the P substrate contact, or the PWC contact. This is how you will draw the layout from the twisted schematic. Now let's see how to draw the layout from the normal schematic. Let's see the normal schematic diagram. Now let's see the layout of a AND or invert gate from the untwisted schematic. Layout of AND or invert from the untwisted schematic. So just in order to refresh, let me tell you the schematic. This is one PMOS. This is the second PMOS. These two were in parallel with the third PMOS. So this is A, this is B, and this is C. These two are in parallel. This is VDD series with this, and just in the opposite you have the two NMOS that is A and B in series which are together in parallel with third input C. Now you have to convert this exactly in the layout form. For example, if this is a NMOS, this is a PMOS, these are the set of PMOS, and these are the set of NMOS. So instead of representing in this format, that is, this was the N well and this was the P diffusion, so instead of this we will represent it as this. So this will be the N well and this will be the P diffusion layer. Okay, now you have to draw the layout in this form. So now let me clear this. So the PMOS P1 and P2 were in parallel, so we will exactly draw like that. We're in parallel with the third one. Then we have this is the N-well layer. Then the P diffusion. These are the P diffusion layer. When you write command, you will write it as pdiff. Okay. Then of the same area, you need the N diffusion layer. So in the N diffusion layer, have the these in series and this is in parallel. So the NMOS N1 and N2 are in series with each other. Together they are parallel with the NMOS N3. Okay, so this is the N diffusion layer. When you write the command, you will write it as NDiff. Then we know this is the PMOS and this is the NMOS. If you want, then you can label it. This is the source, gate and drain. Source, gate and drain. You will not write like this. Source, gate and drain. And over here, these two will be drain. Then obviously this will be source, source, then gate, gate. Why? Because this gate is this drain at drain terminal will obtain the output. Then here this is grounded, the two sources are grounded, so this will be source, this will be drain and this will be gate. Now the corresponding gates are connected. The gate of P1 will be connected with the gate of N1 So if there is no sufficient space, so you're drawing like this. In your layout window, you can draw it properly. Okay, this is your input A. Your input B can be drawn from outside. Okay, before going for B, let's draw the C. This is C. Then you have B. You can draw from here or here. Draw it from outside. Then from here you can connect to this gate. You can understand. Let me draw it with dotted lines. Connect like this. This is your poly layer. This is your second input B. Now after drawing the gate terminal, now draw the source. The inputs are given ABC. Then the sources of the PMOS is connected to VDD. So connect these two. We'll make an extension here since there is no space, otherwise we would have connected like this. Okay, they're connected to VDD, and the sources of the NMOS is connected to ground. Okay, now after this, the drain of the PMOS 1 and PMOS 2 is connected with the source of PMOS 3. So connect. Now the three drains are shorted, so here it looks very untidy, but when you draw the layout, you have the specific width, so design will be much clearer and neater. Then the source is connected with this drain. So this is your metal one. Now after connecting all this is your output. This is your output because output is obtained at the drain terminal. Now place the contacts. First the diffusion contact that is connecting the metal with the p diffusion layer. So this is one p diffusion contact, then the second, third. There were six p diffusion contact. This is the p diffusion contact or the PDC contact. This is again the PDC contact. Similarly, we have to place the N diffusion contact, since we have to connect the metal layer with the N diffusion layer. So this is the N diffusion contact. Okay. Similarly over here, wherever there is connection between the metal layer and the N diffusion layer, there we have to place the N diffusion contact. Why? Contact word means that you have to get the contact. We have to make a contact. So the normally the metal layer is just overlap, but it is not connected. So in order to connect, you have placed the diffusion contact. So this is the N diffusion contact or the NDC. Now after placing the diffusion contact, you can place the substrate contacts. These are placed in the VDD and ground layer. So this is one. You can place it as many as you want. So this is the P substrate contact. The P substrate contact is placed on the N diffusion side. P substrate contact, or you can term it as P well contact, PWC. It's PWC. Similarly over here, you place, oh, this is the poly layer. Not over here, not over here. You have to place in the VDD layer, because usually we place the VDD layer here. So this is the N substrate contact. While writing the command, you can write it as NWC or the N-well contact. So this is the layout from the two-step schematic. It may not look good, but if you draw in the layout, then you can draw it properly. Now let's see the explanation for the truth table. The truth table that we had written earlier. So let's take the explanation for the truth table. Now the first condition for in the truth table was when A is equal to 0. First was when A is equal to 0, B is equal to 0 and C is equal to 0. A0 has P1 and 1, B0 has P2 and 2, A has P1 and 1, B has P2 and 2, C has P3 and 3. That means A is given as input from the gate terminal of P1 and N1, Similarly, B and C. So we know that when input is equal to 0, then PMOS is on and NMOS is off. When input is equal to 1, then PMOS becomes off and NMOS becomes on. It turns on. So when all the inputs are 0, then only the PMOS will turn on. So P1, P2 and P3 will turn on. P1, P2 and P3, they turn on. N1, N2 and N3, they turn off. Okay. When P1, P2 and P3 turn on, then it gets short circuited. When N1, N2, N3 get the turn off, then they get open circuited. Now how do you represent the short circuit? P1, P2. Since P1 and P2 were in parallel, P3 was in series. So it's short circuited. So this is P1. P2 is also short circuited. This is P2. P3. Okay. Now N1, N2, N1, N2 and N3, they are open circuited. This is ground and this is VDD. The output is obtained over here, output Z. Now when N1, N2 and N3 all are open circuited, then certainly this will not work. Now P1, P2, P3, all three are short circuited, so they create a path over here. So the output obtained will be VDD, the voltage gain will be VDD. So Z has a value called VDD, or you can say as high voltage or 1. So when A is equal to 0, B is equal to 0 and C is equal to 0, the output obtained is 1. This is proof. Now let's see the second condition, that is when A is equal to 0, B is equal to 0 and C is equal to 1. Again this is P1 N1, this is P2 N2, this is P3 N3. When 0 0, then P1 will turn on. When the input is 1, then NMOS will turn on. So in this case P1, P2 and N3 will turn on. N1, N2 and P3, they will turn off. So again this is represented by the short circuit. This is represented by short circuit, and N1, N2, P3, when they turn off, it is represented by open circuit. Now P1 and P2 were in parallel and short circuited. So this is in parallel, this is P1, this is P2. They're in parallel and short circuited, while P3 is open circuited. Then N1, N2, they are open circuited. This is N1 and N2. N1 and N2 are in series. This is P3. This is short circuited. This is ground, N3. So from here you can clearly see this is the output Z. You can see that P1 and P2 are short circuited, but P3 is open circuit. So this will block the high voltage. This will block the high voltage. Now N1 and N2 are short circuited, but N3 is N1 and N2 are open circuited, but N3 is short circuited. And this is a parallel connection. So whatever, even if this is open or short, this will not affect since N3 is short circuited. So the low voltage is obtained at the output. So Z is either, we can say, ground or the low voltage or 0. So when A is equal to 0, B is equal to 0, C is equal to 1, then the output obtained is 0. Now let's see the third condition, that is when A is equal to 0, B is equal to 1 and C is equal to 0. So this is again, let me write P1 and 1, P2 and 2 and P3 and 3. Where there is 0, 0, P1 and the PMOS will turn on. So P1 and P3 will turn on. When B is equal to 1, then N2 will turn on. So P1, P3 and N2, they will turn on. P2, N1, N3 will turn off. So this is represented by short circuit and this by open. So now P1 is in parallel with P2. So the one is short circuited, P1, while P2 is open. Then P3 is again short. This is P3, this is P2, and this is VDD. Now N1 is off, N2 is on. This is N1, N2, and N3 is open. This is ground. This is the output Z. Now over here, N1 and N3, they block the low voltage since they both are open circuited. They both are open circuited. In the PMOS, P1 is short circuited, P2 is open. So since P1 and P2 are in parallel, so this open circuit will not affect. So since P1 and P3 are in series with each other, so this is short circuited, then this is 1, then the output obtained will be, this is closed circuited, this is closed circuited. So the output obtained will be VDD through this path. VDD, or you can say this is the high voltage, or you can say it as 1. So when A is equal to 0, B is equal to 1 and C is equal to 0, the obtained output is 1. So this is also now satisfied. The third condition. Now the fourth condition is when A is equal to 0, B is equal to 1, C is equal to 1. So P1 N1, P2 N2, P3 and N3. So 0 means P1 will turn on, 1 means NMOS will turn on. So P1, N2 and N3 will turn on, and P3, N1, P2, P3 and N1 will turn off. So the on will be represented by short circuit, and off when the PMOS and NMOS will turn off, then it is this is represented by the open circuit. So now when P1 is on, so this is represented by the short circuit. This is P1. P2 is off, so this is open circuit. P3 is also open circuit. Now N1 is off, so open circuit. N2 is on, so represented by short circuit. N3 is also on, so represented by short circuit. So this is N3 and this is the output Z. So before looking for P1 and P2, we can see P3 is short, it is open circuited, so it will create a blocking over here. Here N1 will block the flow. This is ground, not this is ground. So since N1 is parallel with N3, this will be obtained in the output. When they're in parallel, it's just like OR condition. This is 0, this is 1, then the output will be 1. So Z is ground, or you can say the low voltage or 0. So when A is equal to 0, B is equal to 1, C is equal to 1, the obtained output will be 0. Now the fifth condition, when A is equal to 1, B is equal to 0, C is equal to 0. So this is P1 N1, this is P2 N2, and this is P3 N3. When A is equal to 1, then N1 will turn on. When inputs are 0, then the PMOS will turn on. So P2, P3 and N1 will turn on. P1, N2, N3 will turn off. So this is again represented by short circuit, and this is represented by open circuit. So now short circuit means P1 is open, so this is open. P2 and P3 are shorted. So this is P3, this is P2, and this is VDD. N1 is short circuited, while N2 and N3 are open circuited. So this is short and N1 is on, shorted, N2 is off, this is also off. So now the output when A is 1, B is 0, C is 0, then the obtained output will be, this is Z, here this is blocked. Here N1 is shorted but N2 is open. So here already there are two blocking. Here in the PMOS, this is in parallel, so this short circuit, this open circuit will not affect. So here it is short circuited, this is short circuited, so the obtained output will be high voltage. So Z is either VDD, or you can say this as high voltage or 1. So when A is equal to 1, B is equal to 0, C is equal to 0, the obtained output will be 1. Now let's see the next case. When A is equal to 1, then B is equal to 0 and C is equal to 1. So in this case, P1 N1, P2 N2, then P3 N3. So P1 N1 will turn on, N3 will turn on, and P2 will turn on. So now you can say P1 is off, so it is represented by open circuit. P2 is on, represented by short circuit. Then P3 is off, open circuit. This is VDD. Now N1 is on, N2 is off, N3 is on, N3 is on. This is N1, N2, N3. This is the output terminal Z. So here P3 is open circuited, P1 is open, so this will block the high voltage. Here N1 is shorted but N2 is open, N3 is short. So since N1 and N2 are in parallel with N3, so this short circuit will not affect. So the obtained output will be or low voltage or 0. So when A is equal to 1, B is equal to 0, C is equal to 1, output is equal to 0. In the seventh condition, when A is equal to 1, B is equal to 1, C is equal to 0. So P1 N1, P2 N2, and P3 N3. N1, N2 will turn on and P3 will turn on. The other three will remain off. So P1 is off, open circuit. P2 is off, again open circuit. P3 is on, so short circuit. This is P1, this is P2, this is P3. N1 is short circuit, N2 is short circuit, N3 is open circuit. So this is ground. This is N1, N2 and N3. So here these two are open, this is short. So even though this is the P3 is on, there is already a blockage over here. Here N3 will block the flow of low voltage, and here N1 and N2 both are shorted. So this is in parallel, so this will not affect, the open circuit will not affect. So the obtained output will be again ground or low voltage or 0. So when A is equal to 1, B is equal to 1, C is equal to 0, then output will be 0. Now let's see the final condition. That is when A is equal to 1, B is equal to 1, C is equal to 1. So that clearly means that only N1, N2 and N3 will turn on while the other will remain turned off. So all the PMOS are represented in open circuit and the NMOS are represented in short circuit. This is VDD. This is P1, P2, P3. This is N1, N2 and N3. So from here clearly you can see that the output will be ground or low voltage or 0. So when A is equal to 1, B is equal to 1, C is equal to 1, then the obtained output will be 0. So now the truth table of OR and invert is being clarified and is being explained.